Good morning, dear student, and welcome to this fourth edition of our numerical method class. Today we are going to talk about the Chebyshev polynomials. In order to set the stage, we first have to present what is a generalized least square method. Remember that in the least square method, we have a cloud of point, which is defined by xi, yi, where I runs from 0 to n, and we want to fit a given function of an arbitrary form, gx equal to the sum on I of c sub I, g sub I of x. In this case, our gi's are functions that are linearly independent, and they map subspace calligraphic G, meaning that any element of G can be written as a linear combination of Ci, Gi, written in this form. So it's a finite dimensional vector space. So from that, it is obvious that the set made of G0, G1 up to Gn forms a basis of calligraphic G. So the least square method, as usual, will consist of minimizing the distance between the vector, this vector, the vector J, the difference between yj and g of x, yi and g of xi. So in terms of minimization, this will be the difference. If you write that in terms of k, it will be yk g of xk. If we substitute xk here, it will be the sum of c I g I at xk. Of course, I being a dummy variable, we can replace it with j and substitute here. So this is what we are trying to minimize, this expression. So this is a generalized least square. As long as we know the element of the basis of G, calligraphic G, then we can perform this minimization and the normal equation will be given by this expression in equation 1.28. So once we solve this, we will obtain the coefficient Cj, because you can see here we have a linear system of n equation in n plus 1 equation in n plus 1 unknown. So the purpose actually, once we have the g's, we substitute in this expression. You can see that these are the coefficient of the matrix, the coefficient matrix. Now the interesting thing here is particularly this expression. This expression here, which is our, this is like our A, Ig. It depends on I and G, so we can call that A, I, G. Which are the entries of the coefficient matrix for the linear system. Now, if you look at this expression, we can look at this as the entries of the vector let us write that properly. If, for instance, we define the vector you can see that these are the components. We have the components of the vector here. This is a vector. The components, since we are summing over k, so the entries are the keys. So this is fixed, and this is fixed. So we can call this G. Yeah. G. Okay, we can write GI. So let's say GI. Let's say that GI here has oh sorry, I have a problem with my writing part, the tablet. It'll be a bit difficult to write anything here. Okay, so if we take this GI as having component GIX, let's say XK, where K run from 0 to M, and we do the same thing. We do the same thing for G sub J. We write that it has a component XK, where K also runs from 0 to M. You agree with me that we can write, because this is a vector in Rm plus 1. So they are all element of Rm plus 1 because we start from 0. Now we can write the norm of this. We can write the norm of each one. We know already that the norm of, if I write, for instance, the norm of this, let's say the two norms square will be this sum. Will be the sum of the absolute value of a square, right, where K runs from 0 to M. So this is the two norm square with this one. And now if we write the dot product of these two, we know that if I have the dot product, we can write that as this transpose times Gj, and this will be equal to what? It will be the sum K running from 0 to M, then this xk jxk. So this is what we have as the dot product, right? So that dot product, we can also write it in this form, comma, right? This dot product. Now, if you look at this, you can see that actually this is a dot product. This is a dot product. If you look at the expression, we have exactly the same. Considering that gi is defined this way, right? That is, we take it as a vector in Rm plus 1. This one similarly, this represents a dot product. Now we know that if you have a dot product, if the dot product is 0, we say that the two vectors are orthogonal. And if the dot product is 1, when we say the dot product is 1, it just means that if I is equal to j, then we obtain the norm. And if the norm is 1, we say we have a unit vector. So if for each I, the norm or the two norm of gi is equal to 1, we say it's a unit vector. Okay, so this leads us to this definition. When the basis has orthonormality property, meaning that the dot product, as you can see here, is 1 when I is different from j. It means that if I is different from j, gi and gj are orthogonal, as I mentioned here with the dot product being 0. Now, when the two are equal and we have 1, it means that the norm is 1. So we have what we call an orthonormality property. That is, we have orthogonality of the element of the basis and the norm of each one being equal to 1. That is the orthonormality property. If that is the case, you agree with me that the coefficient here, the a sub ij, will be equal to the identity. Why? Because along the diagonal, I is equal to j, and when I is equal to j, all the elements along the diagonal are all 1, and the off-diagonal elements are all 0. So it gives us exactly what we call the identity matrix, right? So if we try to write that here, if we can write that there, the coefficient matrix. So let's say the matrix with entry ij, aij, aij will be equal to 1 along the main diagonal and 0 of diagonal. So this is what we call the identity matrix. Now, if you have the identity matrix, our linear system, which is given by this normal equation, if this is identity, we can see, okay, if it's identity in that case, we can see that, we can write it. So this is delta ig, right, which is exactly what we wrote here. That entry, it's delta ig. Now, if it's delta ij and we substitute it here when it's orthogonal, we see that this sum will reduce to, because we are summing here on j, what is changing is j and I is fixed. So when j is equal to I, j equal to I, will have ci equal to this sum. K running from 0 to m, y sub k, g sub I of xk. And this is true for I running from 0 to n. So you can see that there is no need to solve a matrix a dense matrix, right? We have directly the value of Ci. So we have all these unknowns, right? All these coefficients, because that is what we are trying to compute through this minimization problem. So once we know the Ci, we know the function gx. So you can see that if the element of the bases are orthonormal, the coefficient matrix becomes identity. We have directly the coefficient of the gx, the Ci are given directly by this formula. So no need to solve a linear system because the coefficient matrix will reduce to identity. So we have directly the expression of the Ci. So this is what orthogonality or orthonormality property can allow us to achieve. And we will see, because now we were just introducing, so we will, if we are able to find such a basis, right? The G sub I, such a basis like this, that is orthonormal or orthogonal, it will simplify our minimization problem. And that is what Chebyshev polynomial would allow us to do. Okay, so I hope with this one, with this explanation, you are prepared now to follow what we are going to tackle from now on. Okay, now let's proceed. So we are going to define what is a Chebyshev polynomial. We will start from here for the definition. So we can define a Chebyshev polynomial of degree n, or also called a Chebyshev polynomial of the first kind. It is defined by this expression. So this is by definition, Tnx is equal to cosine n cosine inverse x. Or we can say it's cosine n theta, where theta is r cosine x, which is the same as cosine inverse of x. So this is the simple definition of a Chebyshev polynomial of the first kind. So it's a cosine of the subscript n times theta, where theta is the cosine inverse of x, and x is taken in the interval -1, 1. All right, so now we have this recursion formula that can allow us to generate the various expression of Chebyshev polynomial. So this expression can be obtained via this identity, this trigonometric identity. Cosine n plus 1 into theta plus cosine n minus 1 into theta is equal to 2 cosine theta into cosine n theta. So if you allow, we can quickly perform this computation. So we have cosine. We have cosine A plus B, which is equal to cosine A, cosine A cosine B minus sine A sine B. And similarly, cosine A minus B is equal to cosine A cosine B plus sine A sine B. Now, if we add these two, if we add the two, if we call this equation 1 and equation 2, so adding equation 1 and 2 will give us cosine A plus B plus cosine A minus B. You can see that with this negative and positive sign, these two will cancel out. Then we obtain twice cosine A cosine B. Right. Now, if you use this expression and take this to the left-hand side, we have cosine A plus B is equal to 2 cosine A cosine B minus cosine A minus B. Right. So we know that we have as a factor n plus 1 into theta. So if we expand that, it gives us n theta plus theta. So meaning that we can let A to be n theta and B to be theta. So if we do this, A plus B will be exactly this one. So this implies that A plus B is nothing else than n plus 1 into theta and A minus B will be equal to n minus 1 into theta. Now, if you substitute that here, let us call this equation 3. So if you substitute that expression into equation 3, it gives us, it becomes, so this one will be t n plus 1 x, right, which is cosine A plus B, that is cosine n plus 1 theta. This will be equal to 2 cosine A, which is this one, and then cosine B. So I can write cosine B before, that is cosine theta, and then cosine A, which is cosine n theta minus cosine A minus B, which is cosine n minus 1 theta. Now we can transform that in terms of, so this cosine theta, remember that we know that the theta, if you recall, we said that it was cosine inverse or cosine, which I will write directly as cosine inverse x. So if I apply cosine on both sides, it implies that x is cosine theta. So cosine theta is x, so I substitute this one, that is 2x. So this is equal to 2x, and this one is Tn into Tn Tnx minus, and this the remaining term is Tn minus 1 x. So what can we write in the final, as a final result? Tn plus 1 x is equal to this expression. So this is the recursion formula. Tn plus 1 can be written in terms of Tn and Tn minus 1. That is, Tn at the current, if I can say current iteration if you want, n plus 1, can be written in terms of the two previous iteration. That is Tn, because before this you have Tn, and before Tn you have Tn minus 1. So in order to compute T at a given station, or at a given n, we need the previous two values. So it gives us this recursion formula. Okay, so with this we can go back to our slide. So once we have this recursion formula, we can easily so that's exactly what we have. Okay, T0, if we take n equal to 0 and substitute here, it will be cosine of 0. We know cosine of 0 is 1, so T0 is 1. And then when T is 1, if we substitute, when n is 1, we substitute in the formula, we see that cosine of theta, as we saw, cosine theta is x. All right, so we know T0, we know T1. From these two, using this recursion formula, we can generate the remaining terms of the sequence. So we can compute T2, T3, T4, T5, and so forth. Can easily write a computer program to generate T of an arbitrary n. Now, if you look at the expression, you can see that for any n, the corresponding degree of the polynomial is, let's say, if you look at, we take n equal to 5, this is a 5th degree polynomial, n equal to 4, 4th degree polynomial, n equal to 3 degree, and so forth. So for any n, Tn is a polynomial of degree n. And the leading coefficient, as you can see here, is 2 to the n minus 1. Okay, so we are going to look at some properties. Before mentioning the orthonormality property, let us first look at one important result of the Chebyshev polynomial, is that Chebyshev polynomial of degree n has exactly n roots. Now, if you look at this graphical representation here, we have represented 5 different polynomials, starting from 0, t0 up to t4. So in total, we have 5. Now, let us draw the axis properly. Let us expand this a bit. So this is the axis. We have 0 here. That is the x-axis. And the y-axis is given by this. Now, if you look at the graph, x varies from -1 to 1. And now, if you take t0, you can see that t0 is 1. So it's a constant. There's no root. It's a 0-degree polynomial, so there's no root. Now, t1, which is x, this is the graph in yellow. It has exactly 1 root, which is 0. Now, if you look at t equal to 2, this is the quadratic second-degree polynomial. It intersects the y-axis at 2 points. The first intersection, which is negative, the second intersection, positive. Second-degree polynomial has 2 roots. First-degree polynomial, 1 root. 0-degree polynomial, 0 root. Now, if we move to the third one, this is t3. You can see that 1 goes through 0. We have another one here, which is negative. And the third one here is positive. And finally, the 4th-degree one, which is the green one here, has 4 roots, 2 negative and 2 positive. What can you realize? Each time the degree is even, meaning that it's divisible by 2, half will be negative, the other half will be positive. But if the degree is odd, automatically 1 will be 0. The remaining, because if 1 is 0, it means that we subtract already 1 from an integer, from an odd number. What remains is an even number, so we can divide that by 2. So the half of the remainder will be negative, and the other half will be positive. So that is the remark we can draw at this stage, and this can be generalized. So now let us prove the property that Tn equal to 0 implies that Tn equal to 0 implies that we have exactly n roots. So I think that the best way for us to do that is to use a slide so that I take time to explain properly what is going on here. I don't want to overwrite on the slide. So it's better to open a new slide and write properly. Okay. So we are going to write So we are solving t and x equal to 0. So this is equivalent to cosine n theta equal to 0. So in order for us to successfully perform this, we are going to draw what I call the trigonometric circle. Let's use this. So this is our trigonometric circle. We have the x-axis and the y-axis there. So if I take a point M on the circle, this point is M, and the coordinates of M are xy. So what I can do here, I can project, I can project this point on the x-axis, and similarly I can also project the same point on the y-axis. So if I do that, this is y, and this is x. The coordinates of M. And the angle between the x-axis and the position vector OM is given by this angle theta. Right? Yeah. Theta is that angle. So we see that if you want to compute x, we just project M on the x-axis. So from that, we can write that x is what? X is cosine theta, because the radius of this is 1. So r, the radius is 1 for the trigonometric circle. So it's r cosine theta, but r is 1. And similarly, y will be r being what? Sine theta. Okay, now, if I'm solving cosine of an angle to be 0, right? If I want the angle, cosine of an angle to be 0, this is the cosine, the axis, the x-axis that you can see here. X-axis corresponds to cosine. So this is the cosine axis, and this is a sine axis. So meaning that for cosine to be 0, it means that because if I am anywhere on the circle here up to there, and I project on the x-axis, I'll be able to read. But for the cosine to be 0, either I am at this position, let me use the red color and put a dot. Either I am here at that point or I'm here at this other point. So for my cosine to be 0, I have to be here or there. Except this, my cosine will be non-zero. As an example, if I am exactly at the current position of n, except these two, if I am here on the x-axis, the cosine will be 1. Because the length, the value of the cosine will be actually the length, all this length, because it's a circle. If I bring m to this position, the value will be 1. If I'm there, it will be -1. And if I am everywhere else except at these two positions, let's say if I'm there, I project on the x-axis, you see that it will be non-zero. It will be here. That will be the cosine. If I am here, I project on the x-axis, it will be non-zero. So the only way I project on the x-axis and the value is 0 is if I am on the y-axis. Being on the y-axis means I'm either here or there because I am on the circle. So the circle and the y-axis have to intersect. So I can only be on those two positions. Now, how do I quantify the fact that I am at this position or at this other position? The first thing, if the angle is pi by 2, I will be here. So if theta, let me write it here, if theta is equal to pi by 2, cosine theta is 0. And if I'm here, this is 3 pi by 2. If theta is 3 pi by 2, cosine theta is also 0. So meaning that I'm either here or there. Okay. But if I am at this position and I rotate by 2 pi, we know that cosine is 2 pi periodic. So if I rotate by 2 pi, I will find myself at the same position. So meaning that this angle, actually, I can write the first one. Let me call this theta 1 and this theta 2. So theta 1 can also be written as pi by 2 plus 2k pi. I can rotate in the positive, which the trigonometric direction is this one, it's positive this direction. Or I can also rotate in the other direction. So that's why this k can be positive or negative. Now for the second one, I can do the same thing. 3 pi by 2 plus 2k pi. So if I'm here, I can rotate by 2 pi in the positive or negative direction. I will find myself at the same position. So these are the possible. You have infinitely many. For each value of k, you have these two angles. So we can combine these two into a simple angle, which I will call just theta. If I combine the two, and what will be that angle? It will be 2k plus 1 into pi by 2. Okay, so can we check k in z? So can we check that? Can we check to make sure that it covers both? Okay, so if k is equal to 0, here we have pi by 2, which is this one. If k is equal to 2, I say 0. Now, if k is equal to 1, this will be 2 plus 1, 3 pi by 2, which is this one, 3 pi by 2. So you can see that by changing k from 0 to 1, I take one value of theta 1 and the next will be theta 2. Now, if I take k equal to to 2, will I be here? Let's say k equal to 2, that will be 5 pi by 2. Now, if I take this one to be 1, if k is equal to 1 here, same denominator, 2 times 2, that will be 4 plus 1, 5 by 2, which is exactly this one, and so forth. So this one will combine the two. So now if we come back to star, let's call this equation star. After this explanation, we can see that star now we will call, instead of calling that angle, because I'm solving for theta here, now we have n theta, because it's n theta that is 0 instead of theta. So I will replace it with n theta equal to that. So star, from star, we can see that therefore star implies or is equivalent to n theta. Of course, because it depends on k, I can subscript it with k. That will be equal to what? This expression, 2k plus 1 into pi by 2, where k is in fact is an integer, positive or negative. Right. So from here we have this result. What we want x, right? But x is hidden here. But before that, we divide. So this is equivalent to the fact that theta, depending on k, will be 2k plus 1 by pi into pi by 2n, because we are dividing by n. Of course, k in z. But now we have to impose the condition on theta, right? Because this theta comes from the definition of cos inverse. And cos inverse is defined for theta in the interval 0, pi. Theta is defined in the interval 0 to pi. So with theta in the interval 0, pi. That is the definition of cosine inverse. So this is by the definition of arc cosine, arc cosine or cosine inverse. So it's by definition that this has to be in the interval 0, pi. Now, if we impose the fact that it is in that interval, so we can write that this will be right. Now you see that this will bring a restriction on the value of k. So if you succeed, if you solve this inequality, we will end up with k taking the values 0, 1, 2, up to n minus 1. So this is a homework that you should perform. You should do that. You should do this homework. Now, if k is here, if you count how many k's, so if you count this, you will see that we have exactly n. So we have in total n different values of k. All right, now what is our expression for the solution itself? Because we are still, this is the subscript of k. This is what the range of k has to be, but we still need to find the root. So this is theta, but what is theta? Theta k is cosine inverse xk. So that this cosine inverse of x is equal to that expression, that is 2k plus 1 into pi by 2n. Now, if you want to get the xn, we apply cosine on both sides. So this will be equivalent to x sub k equal to cosine of what? 2k plus 1 into pi by 2n, where k takes the values 0, 1, 2, up to n minus 1. So in total, we can see that there are exactly n distinct roots. And that's what we wanted to prove. So this ends the proof. Okay, so we are done. We have exactly n distinct root. Okay, back to the least square problem, because remember I introduced the least square problem where the intention was to fit an expression of this form to a set of data points where the j sub k were element of a vector, I mean the basis of a vector space. And we saw that if the gk's are orthogonal or orthonormal, the least square problem becomes simple to solve. Now we can take the gk to be the tk's, right? Where k runs from 0 to capital N. So you see that we saw that for each k, tk is a polynomial of degree k. So if we sum a polynomial of degree less than or equal to n, because the final here will be tn. If you replace that, you can see that this gx becomes pn is a polynomial, because we write pn because if we sum polynomials, right, a linear combination of polynomial less than or equal to n will be of degree n. So that's why gx is written by, is replaced with p sub n to indicate that it's a polynomial of degree n. Okay, now we are going to look at the orthogonality property of the Chebyshev polynomial. And for that purpose, we have two possibilities, the discrete case and the continuous case. We can start with the continuous case. This is the discrete case given by this result, which is actually a polynomial. Actually, anyway, it's even the it's an assignment that I gave you. Okay, so this is a property, or the property of the Chebyshev polynomial. So you can see that when m is different from n, we have this dot product that gives us 0. But when m is equal to n, this gives us n plus 1 by 2. We know that this is a norm square. If m is equal to n and they are all different from 0, we have this result. But if they are all equal to 0, we have a similar result, but it's not divided by 2. So it's twice this result. So you can see that this is not 1. So it cannot be normal, but it will be only orthogonal. So that's why we say it is orthogonal, but not orthonormal. Orthonormal is if when m is equal to n, we have 1, 1, right? We have 1, but this is not the case. It is different from 1, so it's orthogonal. Okay, this is for the discrete case. Now for the continuous case, is what we skip in the beginning, is this case. Instead of having a discrete point, if you have continuous point, the sum is replaced with an integral. But here we have a weighted integral. So if we define this to be our dot product of Tn with Tm, we can see that when the two are different, we still have 0. When they are equal, m is equal to m and equal to 0, it is pi. But when they are non-zero, it's pi by 2, which is still different from 1. So it will be orthogonal, but not normal. Okay. Okay, so this is the case of the discrete point. So the xk are discrete point, or the interval negative 1, 1. We saw that these are roots. Okay, for this we take our xk to be the roots. I think it has been mentioned here. I did not stress on that, but all the xk's here are roots. Sorry. Xk here are roots of t sub n plus 1. We know that t sub n plus 1 has capital N plus 1 distinct root. And they are given by this. So how do we come about that? We just, from this, we just take, we let this n minus 1 equal to capital N. And if we count the total number, we know that we have capital N plus 1 roots. If you have capital N plus 1 root, it means that the corresponding polynomial. Actually, we know that the Cn from here, if n minus 1 is equal to capital N, we can find that n is capital N plus 1. So this will be what? The root of t n, which is t capital N plus 1. Oh, sorry, capital N plus 1. And if we replace n here as capital N plus 1, we expand, 2n becomes 2 capital N plus 2. And that is exactly what we have here in the denominator, and carry on from 0 to capital N. Okay, so those are the xk that we use in this formula. to prove the orthogonality of the Chebyshev polynomial, discrete Chebyshev polynomial. I mean, Chebyshev polynomial at discrete point. All right, so if we go back to the least square problem, as I mentioned, it becomes easy to compute the various coefficients, the CJs. These are the CJs. Remember, we said that if we were dealing with discrete, I mean with orthonormal, we saw the expression here. But what if it's no longer orthonormal? If it's not orthonormal, it means that it's a, of course, not that it means it is. In the case it's just orthogonal but without being normal, then this CJ will be multiplied by a given factor, and those factors we know already what each factor will be equal to. So if I is equal to j along the diagonal, we'll be having pi by 2 here or pi, depending, because for this case, instead of 1, we have pi or pi by 2. So let's look at those cases. So you can see here, if m is equal to n but not 0, okay, I say pi or pi by 2, that is in the continuous case, but currently we are dealing with the discrete. Sorry for that. So it will be n plus 2, n plus 1 by 2 when m is n but not 0, but if they are both equal to 0, it will be n plus 1. So in the equation above, we can do the same thing. So let's take this case where m is equal to n equal to 0. You can see that the factor of Cj or C whatsoever, C0, because j will be 0, will be n plus 1, right? In the expression above where we only got Cj. So m equal to n. That is for the subscript here. Okay, so let's see what that would correspond to in terms of j. Okay, so this is where we are. We call this AIJ. And we are summing here. And we say that if I equal to j equal to 0, because we took this to be, and so we are looking at the subscript of t. Subscript of t is actually the subscript of g. So if they are all equal to 0, because what varies here is j. So when j would take that value, because I is fixed, You can see here I is fixed and j is varying. So when j will take the value of I, which is 0, this will be C0. So from that, we can see that here we have C0. And this one, we saw that this will be n plus 1 by 2 when they are all equal to 0. And this will give us the summation, this one. Okay, let me, what is yk? Okay, let's write it first like that, yk. And this is t, ti as is 0, so that will be t0. Of course, we know that t0 is 1, right? t0 of xk. K running from 0 to m. But this is, what is yk? Anyway, we can still find what that is. So at least we know already this value. Now, if I is equal to j but non-zero, so the case where I is equal to j but non-zero, we know that the factor here now will be n plus 1. So we can do the same thing. The factor now becomes n plus 1. I hope it's not a converse, but we can still fix it. So they are equal but not 0. So I can replace it with cj or ci because they are equal. And then I will have t something here. That something will be exactly that summation. We have k here, and this is t ti, and I is equal to j, so we can replace that with j. Tj xk, k running from 0 to m. So you can see that we can now, to get our ck, we just multiply by the reciprocal, that is 2 by n plus 1, and here we divide by n plus 1. And whatever the yk will correspond to, we'll substitute it here. Now, if you scroll down, you can see we'll get exactly the results here. Okay, so this is okay. So the for 0, it is actually n plus 1, right? It's n plus 1, not, yeah, yeah. N plus 1 is for 0, and n plus 1 by 2 is for non-zero, right? So I can change that. Yeah, I can change that there. 0 is for n plus so this one is not divided by 0. So for 0 here, this is n plus 1, and here it's n plus 1 by 2. So we can get directly here that C0 will be 1 by n plus 1. And then we have the sum here running from 0 to m, yk, where yk is f of xk. You can replace that by f xk. Obviously, if you are approximating a function f, right? And here, this for cj, this will be 2 by n plus 1, the same sum, f of x k into tkx. Sorry, that is tj, same jj xk. C J X K, right? K running from 0 to M. Okay, so these are the values that we will find so that's exactly what we have here. Exactly. C sub j, T sub j, and then we have f of xk and summation to M, where M is our is the degree of the polynomial here. So this is a polynomial. The sum here goes up to n, so we replace that with a capital N. So that is it. So at the same time, we have just proved the theorem. We have the proof of the theorem. You see that it's not that different. Once you understand the least square problem, as I stated in the beginning, with the orthogonality property, you just go there and substitute. You see that we obtain exactly the same results here. As an example, this is an example, which is just a simple substitution. And I think we'll stop here. For now, the video has been long. Thank you for your kind attention. God bless you, and see you in the next video. Enjoy and stay tuned. Bye-bye.